Unit 1, Tools of Geometry, Part 1, Angles and Segments. Using the handout given to you, or if you do not have this handout, then just model it accordingly in your notes. We're going to start off by talking about a point. The model for a point is a dot, and then it's usually labeled with a capital letter next to it. So as we just stated, it's drawn as a dot. It's named by point P, which in most cases we said a capital letter. Some facts about it: it doesn't have shape or size. So even though it looks like a circle, it's not. It's just a point. There's no shape or size. And the words or symbols, we either say P or we refer to it as point P, or whatever letter it's labeled as. A line is modeled like this. It's drawn with an arrow at each end. It's named by either 2 points or a lowercase letter. Facts about it: it doesn't have width or height. It only has a length. And it's either named by its points, A, B, with a line above it that has 2 arrows, or as a line, in this case L, a lowercase letter. A plane, it's drawn usually as a parallelogram, and then the parallelogram is given 3 points. So let's say C, D, E. And then the plane itself is named by a capital letter. So let's say S, and it's normally written in the corner, no point next to it. So as we said, it's drawn as a parallelogram. It's named by either 3 points or by the capital letter. Facts about it: it goes on infinitely. In every direction. So in other words, I know it looks like a parallelogram, but it's actually continuing infinitely in every direction. Think of the coordinate plane. We graph equations, but we only show like a snapshot of the coordinate plane. Another fact about it is that it doesn't have height. Have height. Words or symbols, we could call this plane CDE, or we could just call it plane S. So you could name it by the 3 points that are on the plane, or you could name it by the capital letter that represents the plane. A segment is modeled like this. It's drawn with 2 endpoints. It's named by 2 capital letters. Some facts about it would be, just like the line, it doesn't have height or width. And words or symbols, we draw it with a segment above and then AB. So you name it by its 2 points, but keep in mind, unlike the line, there's no arrows here. You don't have to draw the actual endpoints though. Array is modeled like this. It's drawn with 1 endpoint and 1 arrow. It's named again by 2 capital letters. It can also be named just like a line is. We can call it Ray L or Ray R or whatever you'd like to, but by 2 capital letters generally. Again, it doesn't have a height or a width. We're just working with length here. And you draw it just like you see it. There's an arrow on one side, and it's Ray CD. Opposite rays would be drawn similarly to when we drew a line before. Say this is point O, this is point A, and this is point B. Opposite rays are drawn as a line basically with 3 points. At least 3 points. It's named by, in this case, it's going to be 2 sets of capital letters that share a common point. So let's write 2 sets of capital letters. Fact about it is that the rays share a common point and point in opposite directions. I'm just going to abbreviate directions because I'm running out of room. Directions. The words and symbols, well, I would say Ray, OA, and Ray, OB, always start with the end point and then go towards the point that's pointing towards the arrow or closer to the arrow, are opposite rays because they share a point and they point in opposite directions. Keep in mind, however, that if I had a situation, let's say this was point O, and point A was over here and point B was over here, these could be 2 rays, OA and OB, but they're not opposite. In order for them to be opposite, they need to be pointing in opposite directions. So if B was over here, then they would be opposite rays. It's going to be a straight line that makes these up. Now, just a few pieces of information about lines. Lines can be, they could be parallel. We'll elaborate on that in a second. They could be perpendicular. They could be intersecting. Or they could be skew. You might need some different colors for this worksheet in order to fill in all of this information. It's easier to see when it's written in different colors, but that's up to you. Parallel lines are on the same plane. And they don't cross, they never intersect. So just as an example, I have my set of parallel lines, and they're usually labeled, they should be labeled if they're parallel, with a set of arrows on the lines to represent that they are in fact parallel, they don't just look parallel. Perpendicular lines also are on the same plane, but they intersect at 90-degree angles. Now if I were to represent this, I would draw two intersecting lines, and then I draw a little box in one of the corners, and that would represent that they were perpendicular lines. Intersecting lines also are the same plane. Now perpendicular lines are a type of intersecting lines. They intersect, they cross. Not necessarily at a 90-degree angle, but it could be a 90-degree angle. Finally, skew lines are on different planes. Now this is a little bit hard to draw. They're on different planes. So let's say I had one plane here and one plane here. I'd have one line on this plane and one line on this plane. Those are skew lines. They don't cross. These lines do not cross because they're on different planes. It's like being in two alternate dimensions. You're never going to meet in that dimension. Now planes can be parallel, perpendicular, or intersecting. Now parallel planes don't cross, they don't intersect, and you could just draw them like this. Two separate planes not crossing. Perpendicular is where it gets a little bit harder to draw. They cross to form a 90-degree. It's called a dihedral angle. We're going to define that at the bottom of this worksheet in a second. A 90-degree dihedral angle. Now to draw this, I'm going to do my best to draw one plane. I'm going to dash this line and you'll see why in a second. And another plane. And then I'm just going to label it with a little, just like we did with the perpendicular lines, a little box in the corner. Now if you just move down to the bottom of the page so we can quickly define a dihedral angle. A dihedral angle is the union of two half planes with a common edge. Another name for a dihedral angle would be a plane angle. It's the angle that two planes are making. Finally, we have intersecting planes. Intersecting planes cross to form a dihedral angle. Again, I'll do my best. In this case, they're not perpendicular, but that doesn't mean it makes it much easier to draw. And my other plane crossing behind, so a dashed line, and then crossing in front. Now, intersections of lines. Lines intersect at a point. So if I have line L and line M, they intersect at point P. So lines intersect at a point. Planes, however, planes intersect when they're they're intersecting planes like this at a line. So in a different color here, you might want to draw this line. Keeping in mind that the planes do go on infinitely, so there are arrows on that line. We're just representing it with two parallelograms intersecting. Collinear means on the same line. Examples here would be R, S, and T are collinear points. Or you could say P, Q, and R are collinear points. There are other ones as well, but those are just two examples. Coplanar means on the same plane. So if we look at plane R, we could say that point F, D, and B, and G are coplanar. Or we could say C, D, A, and B are coplanar. Points B, D, and A, if you notice here, are on both planes, so that's why we have some repetition here in the D and the B points. So that can happen sometimes because in this case they're intersecting. Now we're just going to do some examples, making sure we can find parallel skew lines, parallel planes, and so forth. Do your best to copy this diagram at the right. Try using the different colors that they represent here. An easy way to draw this cube shape, just for your own notes, is to draw a square, or kind of a rhombus in this case, and then connect the vertices. A little sloppy on the iPad, but it's one way that you could possibly draw it. So looking at this diagram, we're going to look for some parallel lines first, keeping in mind that parallel lines must lie on the same plane. Well, we can see some that are highlighted for us already. If this is point A and this is point D, this is point B and this is point C, they're both on this top plane if we're looking at it as a cube, even though it's really representing a bunch of different planes intersecting. We could say that line AB, or AD in this case, this is the symbol for parallel to line BC. There are a lot of other ones here as well. We could say AE and BF are parallel. We could say AB and CD are parallel. Keep in mind you can also name them as line DA is parallel to line CB. That means the same exact thing, so you don't have to write that multiple times. Now, skew lines are on different planes. So if we look at line AE, what could we say is skew to line AE? It has to be going in a different direction, and it can't be on the same plane. So I couldn't say line AD, that wouldn't work because they share this left-hand plane. So they are technically on the same plane, they're even intersecting. I also couldn't say line CG because if I were to draw an additional plane cutting through the center of this cube figure as we're representing it, they could possibly be on the same plane, so they cannot be skew either. However, I could say line CB. They fall on two different planes, they're going in two different directions, so line AE is skew to line BC. Now, parallel planes, keep in mind, if they're not labeled with a letter, the different planes, then we have to represent it using 3 points. So parallel planes, think of a cube. Even though, again, this is just a representation, the top and bottom are parallel, the left and right are parallel, the front and back are parallel, so we could pick any of those. Let's say plane ABC, so the top is parallel to plane, the bottom, EFG. You could use all 4 letters to represent the plane, but you only need 3. Remember, parallel lines are coplanar, so which planes contain AB? Just really want to stress this factor. You can see in this diagram, AB and GH, there is a possible plane cutting through the diagonal of this 3-dimensional figure that we're using to represent a bunch of planes together. So parallel lines are coplanar, which means which planes contain AB? Well, AB is contained by plane ABC, so the top, plane ABG, which is that diagonal, plane ABE, which is that left-hand side of this 3-dimensional figure, which means that in order for a line to be parallel to AB, we would have to find a line that's parallel that lies on those planes. Now, just to quickly fill in a few examples of these properties and postulates, if you have this worksheet from class, then you just have to fill in the examples, maybe add in some notes if there's things that you're having trouble with, but if not, you have a little bit more copying to do. We're going to start off with the reflexive property. A quantity is congruent or equal to itself. We can see that by A equals A. An example of that would just be to show a number is equal to itself. Now, when we're talking about geometry, we would show the length of a line segment is equal to itself. Well, when you're talking about the length of a line segment, you're not going to put the line over the top. You're just going to say that AB equals AB. Now, the symmetric property, if A equals B, then B equals A. In terms of algebra, we would always say if X equals 3, then 3 equals X. It doesn't matter the order that you write it in. In terms of geometry, the length of AB is the same thing as the length of BA. The transitive property, if A equals B and B equals C, then A equals C. Well, again, in terms of algebra, we would say if X equals 3 and Y equals X, then Y must equal 3. In terms of geometry, we would say, well, if AB is the same length as BC and BC is the same length as CD, then AB must be the same length as CD, and that's going to be our transitive property here. The addition postulate says that if equal quantities are added to equal quantities, the sums are equal. So again, in terms of algebra, we used to say that if you had an equation, let's say x equals 3, but you added 2 to each side, it would still be equivalent. We're going to be doing the same thing here in geometry. If I know that 2 segments are equal, adding a segment to each side still makes them equal. So this is my addition postulate. My subtraction postulate, again in algebra, if x equals 3 and I subtract 2 from both sides, it's still going to be equal. It's similar in geometry because if I know that AB equals BC and I subtract CD from both sides, I know that it's still a true statement. Multiplication postulate, again in algebra, if I knew that x equals 3, then 3 times x has to still equal 3 times 3. Even if I multiply both sides, it's still going to be equivalent. It's the same thing for algebra, for geometry. Also, doubles of equal quantities are equal. So you could either say it as you're multiplying both sides by 3, or you're multiplying both sides by the length of another segment, but it's usually in geometry going to be talking about doubling each side, especially when we start talking more about midpoint. So let's say if I knew that the length of AB equaled the length of CD, then twice AB must equal twice CD. The division postulate, again in algebra, if x equals 3, then x divided by 2 must equal 3 divided by 2. Same thing's going to be working in geometry, but again we're going to see a little bit more halves of equal quantities are equal. So if AB equals CD, then half of AB must equal half of CD by the division postulate. Or if you're explaining yourself, you could just say halves of equal quantities are equal. The substitution postulate, a quantity may be substituted for its equal in any expression. We saw a lot of the time if you had something like x equals y, and then you had x plus 3, that's the same thing as y plus 3. So we would substitute it into an algebraic equation or expression. In the case of geometry, sometimes you'll have that AB equals CD, and maybe you'll have two lengths being added together, like AB and PQ. That's the same thing as saying CD plus PQ. So you can actually take that CD and plug it in where AB was. The partition postulate states that the whole is equal to the sum of its parts. So here we have some good examples. Also the betweenness of points, so AB plus BC equals AC. It's easier to see this when you're actually talking on a line. If this is A, B, and C, they're saying that AB plus BC equals AC, which makes sense because they're sharing a point. You'll notice that in some of the examples up here I had where they shared a point. The angle addition postulate works the same way. The measure of angle ABC plus the measure of angle CBD equals the measure of angle ABD. So keep in mind here, just like when we're adding or we're talking about equivalency of line segments, when we're talking about equivalency or adding angles, you write it as the measure of the angle rather than just the angle. So if I had angle A, B, C, and angle C, B, D, I know that when I add these two angles, I'm going to get that whole angle. So the partition postulate says that the whole is equal to the sum of its parts, so you can either use it working forwards, where AB plus BC equals AC, or you could work backwards, saying that AC has to be equal to its parts, and that's by the partition postulate. Some postulates and theorems that we can work with. I'm going to be zooming in so you can write the examples. Again, if you have the worksheet, it's less writing in this area, but I'm going to be zooming in to make it a little bit bigger, so I'm going to be writing in a little bit of a different area. Postulate. A line segment can be extended to any length in either direction. So basically, if I had AB, this is like just taking a snapshot of the whole line, which could be extended in either direction. These are all postulates, theorems, and corollaries that you can use when we're doing proofs, just to make them a little bit easier. Through two given points, one and only one line can be drawn. Well, we know that 2 points determine a line. So if I have 2 points, A and B, there's only one line that can be drawn, because we know that lines are straight. We're not going to be curving it. That wouldn't be a line. There's only one line that can be drawn, and we use that by saying 2 points determine a line. 2 lines cannot intersect in more than 1 point. Again, if I have 2 lines here intersecting, I can't have curved lines. They're always going to be straight because we're talking about lines. So I can't also have this intersect over here. They're only intersecting in that 1 point. One and only one circle can be drawn with any given point as a center and the length of any line segment that's given as a radius. So if I tell you that this is the center and that the radius is 3 units or 3 inches or whatever the measurement is long, there's only one circle that can be drawn to those specifications. At a given point on a given line, one and only one perpendicular can be drawn to the line. So if I have this line and I'm picking a specific point, only one line can be drawn to that line that's perpendicular. Because again, any other line would not be making a right angle. It has to make a right angle in order for it to be perpendicular, so there's only one line that'll be able to do that. From a given point not on a given line, one and only one perpendicular can be drawn to the line that goes through that point, which again makes sense. It's got to be just one line that'll make that a right angle. Otherwise, any other line that includes that point won't hit the other line at a right angle. The distance postulate says that for any two distinct points, there is only one positive real number that is the length of the line segment joining the 2 points. So any two distinct points, so they're different points, there is only one positive real number that is the length of that. In other words, this can't be 3 inches long and 4 inches long. There's one distance and that's it. The shortest distance between 2 points is the length of the line segment joining these 2 points. It's like when people used to say the shortest distance between 2 places is a straight line. So in other words, I don't want to be doing a whole circle curve going around to get to that point. It's a straight line, the length of that line segment. A line segment has one and only one midpoint, and we will be talking more about this, but if I have a line segment AB, there's only one point that represents the halfway mark, the midpoint of that line. Same thing with an angle has one and only one bisector. There's only one ray that is going to perfectly bisect this angle. And keep in mind when you're talking about a midpoint cutting 2 lines in half, this shows that the 2 halves are equivalent, and this shows that the 2 angles are equivalent, that they have the same number of curves, or in this case, dashes. A lot of these are pretty straightforward, but if 2 angles are right angles, then they're congruent. So obviously 90 degrees has to be congruent to 90 degrees. If 2 angles are straight angles, then they're congruent. Straight angles are 180 degrees. So obviously, even if I were to go in the other direction, 180 is always equal to 180. So we say the angles are congruent, the measures are equal. If 2 angles are complements of the same angle, then they are congruent. So in other words, let's say I had a 60-degree angle, and then I had an angle over here that was 30 degrees, and an angle over here that was 30 degrees. Both of these are complementary to that 60-degree angle because they add up to 90, so that means that they have to be congruent to each other. In other words, there's only one measure of an angle that will make it complementary. So if I start with a 60-degree angle, it has to be a 30-degree angle in order for it to be its complement. So if they're both complements to the same angle, they must be congruent to one another. Likewise, if 2 angles are congruent, then their complements are also congruent. So if I started off with 2 60-degree angles, and something told me, oh, well, this is the complement of this angle, then I know this must be the complement of the same angle, and those complements have to be congruent. If 2 angles are supplements of the same angle, then they're congruent. So if I start with an angle that's 100 degrees, I know that if I have 2 separate angles, they have to both be 80 degrees. They have to both be congruent. If 2 angles are congruent, then their supplements are congruent. So if I, in reverse, started with the 2 80-degree angles, those are 2 congruent angles, which means their complement, over here would be the 100, has to be congruent to the complement of the other angle, which also would have to be 100. If 2 angles form a linear pair is supplementary angles, but they're adjacent. So like if I were to have a 100-degree angle over here and an 80-degree angle over there, if 2 angles form a linear pair, they're always supplementary. Linear pair means supplementary and adjacent. If 2 lines intersect to form congruent adjacent angles, then they're perpendicular. So if 2 lines are intersecting to form congruent, so equal measures, and adjacent, meaning right next to each other, then they have to be perpendicular. Otherwise, those 2 angles that are adjacent would not be equal to one another. They'd be supplementary if they're forming a straight line. The right angles are also supplementary, but if they weren't perpendicular, it would be like a 100-degree angle and an 80-degree angle. They would not be congruent. It has to be perpendicular for the two adjacent angles of intersecting lines to be congruent. If two lines intersect, then the vertical angles are congruent. You could always use this. If you have intersecting lines and it's stated that they're intersecting, the vertical angles will always be congruent. Any geometric figure is congruent to itself by the reflexive property. So if I have a square ABCD, it's always going to be congruent to itself, ABCD. A congruence may be expressed in either order. This is the symmetric property. So I could say that AB with the line over it is congruent to CD with the line over it, because congruency, we're always using that. Or I could say that CD is congruent to AB. It means the same thing. Two geometric figures congruent to the same geometric figure are congruent to each other. This is just our transitive property again. We can talk about it in terms of squares, parallelograms, or we can talk about it in terms of line segments. If AB is congruent to BC and BC is congruent to CD, then AB has to be congruent to CD. Again, please keep in mind when you're talking about congruency, if we're talking about line segments being congruent, it has to be written like this. Angles are congruent. You have the angle measure in front. If we're talking about equivalent, an equal sign, you lose the line. Equivalent angles, you now have an M in front. So keep that in mind. Notation is definitely very important. The distance between points A and B is the absolute value of their coordinates, or the absolute value of the coordinate A minus the coordinate B. You write the solution as AB equals, and then whatever the measure is, or you can say the length of the line segment AB is, and then again whatever it equals. So for example, let's say in this number line, I'm going to number every other one just to make it a little easier. And let's say I have point A here and point B here. Well, this point is on -5 and this point is on 3. So the distance between them, you can count on the number line, or you can just do the absolute value of -5 minus 3. Well, -5 minus 3, if we do keep change, that's going to give me a -8, and the absolute value of -8 is +8. So you can write it as AB equals 8 units, or you can write the length of AB, so it's a little bit longer, is 8 units. Make sure you always label with your unit of measure. The segment addition postulate, just to see it more on a number line. If you have 3 points, A, B, and C, all of which are collinear, and they're collinear because they're on my number line, which is a line. B is between A and C, then AB plus BC will always equal the whole thing, AC. Congruent segments. So if I labeled this segment A, B, and this segment C, D, to show that they're congruent, I put the same number of dashes on them. So this shows me that AB is congruent to CD. You could also write it as their measures are equal. The midpoint of a line segment is a point that divides the segments into two congruent segments. A point, line, or ray, or other segment that intersects a segment at its midpoint is said to bisect the segment or be the segment bisector. So let's say I have line AB. In order to find the midpoint, I would take the value of A, add it to the value of B, and divide by 2. So you're finding the halfway point if you're talking about on a number line or something like that. So in order to find the midpoint, let's say this is point M, you would add them up, divide by 2, you're finding the average. if you have a line, array, something that's going through that point, that's said to be the segment bisector. So in this example, the first one, if a line segment has a midpoint at 8, so this is where my midpoint is on the number line, and one endpoint is at 7, so let's just say this is point A. Where is the other endpoint? Well, I skipped a line in between just to spread things out a little bit so it's easier to see. But if we know what the midpoint is, and we know that this distance is 1 unit, the distance to the other endpoint must also be 1 unit. So that means point B has to be at 9. So the other endpoint would be at 9 on the number line. In the next example, if a line segment has one endpoint at -3, so let's say that's point A, and the midpoint of the line segment is at 3.5, where is the other endpoint? Well, I didn't skip any lines, I just only numbered by 3s, but so 3.5 would be here for the midpoint. This distance is going to be 6.5, so that means if I add 6.5 to this, that's my 0.5, and then 1, 2, 3, 4, 5, 6. That's going to be at 10. So that means my other endpoint is at 10. The points P, Q, R, and S are shown as points on a number line. We want to find PQ when there's no line above it. It's looking for the length. PR, QR, RS, PR, QS, and PS. I'm just going to write the answers above, but please write out the question and draw the number line so you have examples in your notes. First, looking at PQ, we can see here from -4 it goes up 1, 2. So PQ is 2 units. We can say PQ equals 2 units. PR, 1, 2, 3. So PR is 3 units. QR goes up 1. So QR is 1 unit. RS, 1, 2, 3. So RS is 3 units. PR, 1, 2, 3. So PR is also 3 units. I'm just going to write this there to save some room. QS, 1, 2, 3, 4 units. So QS is 4 units. And finally PS, 1, 2, 3, 4, 5, 6. So PS is 6 units. Now the other way to do this would just be to take that number, so P is at -4, S is at 2, find the difference between them, and then take the absolute value of that, and it's the same thing, but when you're given the number line, it's easy enough to just count. Part B wants to know what the midpoint of PS is. Well, if this is P and this is S, we're going to do, for the midpoint, -4 plus 2 divided by 2. That's going to give me -2 divided by 2, which is -1, so that means point R. Finally, it wants us to show that PQ plus QS equals PS. Well, the measure of PQ, we said before, is 2 units. The measure of QS, we said before, was 4 units. And PS we also found, which was 6 units, and 6 does equal 6, so that is true. If Q is the midpoint of PR, what are PQ, QR, and PR? So let me first label that this is point P and this is point R. Q is going to be my midpoint. That means that PQ has to be equal to QR. This also means that if I double PQ. It must equal PR, because if this is half and this is half, doubling it would give me the whole. Or I could double QR, and that would give me PR. Or by the segment addition postulate, PQ plus QR has to give me PR. When you're talking about angles, an angle is formed by two rays with the same endpoint. So here's my same endpoint. The rays are the sides of the angle, so this is one ray and this is the other ray. The endpoint is the vertex of the angle, so this is the vertex of my angle. Here I have the interior, so the inside of the angle, and the exterior, the outside of the angle. A straight angle always will equal 180 degrees. So the measure of this angle is 180 degrees. An acute angle is always greater than 0 degrees, but less than 90 degrees. A right angle is always equal to exactly 90 degrees, and we've shown how you label that with the box in the corner. And an obtuse angle is always greater than 90 degrees, but less than 180 degrees, because if it were equal to 180, then it would be a straight angle. Congruent angles we've shown. If this is point A, the vertex is B, and this is point C, so I have ray BA and ray BC. And this is point D, this is vertex E, and this is point F, so I have ray EF and ray ED, each forming angles. I would show that they're congruent by marking them with the same number of curves. I could write that angle ABC is congruent to angle DEF. I could talk about their measures being equal, and all I'd have to do is put an M in front of the angle and change it to an equal sign. By the angle addition postulate, if point B is on the interior of AOC, so if I have angle AOC and point B is on the interior of AOC, then if I were to draw a ray through it, the measure of angle AOB plus the measure of angle BOC would equal the measure of angle AOC, just by the angle addition postulate, just like when we were working with the segment addition postulate. Adjacent angles are angles that are next to each other that share a common ray. So these angles would be adjacent to one another. If it's on a straight line, then that just means that they're also supplementary, but adjacent just means that they share a common ray. Vertical angles are angles that are across from one another when intersecting lines form them. Complementary angles have to add up to 90 degrees. Write as much as you need to for these. If you know what they are, then just draw a diagram, but if you need to write more, then elaborate. Now, supplementary angles add up to 180 degrees. Linear pairs specifically are also adjacent, and they add up to 180 degrees. Now, in terms of looking at lines and talking about angles, you can always assume adjacent angles so you can see that they're touching. You can always assume if two angles are adjacent and supplementary as long as it's a line and it's told you that it's a line. And you can always assume vertical angles, again, as long as they tell you that they are two lines, because you don't want, just as an example, for something to be curved and then be a line. They need to tell you lines AB and lines CD or something along those lines. That way you can assume vertical angles. Don't you dare assume, because you make something out of you and me, congruent angles or segments. You can never see two angles and say, oh, well, those look like they're the same measure, so they must be congruent. Same thing with two segments. You can't say, oh, well, they look like they're the same. It needs to be told to you that they're congruent. You can never assume right angles. Just because something looks like it's 90 degrees, it might be 91 degrees. You can't assume that. And you also can't assume complementary angles. You can't assume things just by saying they look like this type of angle or segment. An angle bisector is, again, a ray that divides an angle into two congruent angles. We mark it by showing that those pieces are congruent. If angle ABC is bisected by BD, so we can use this to represent it, angle ABC is bisected by BD, which is a ray. If the measure of angle ABD, which is this angle here, is 3p minus 4, and DBC, which is this angle here, is 4p minus 16, what type of angles are they? All we have to do, since that's the bisector, is set them equal to one another. So 3p minus 4 must be equal to 4p minus 16. Get the variable to one side, so I'm going to subtract 3p from both sides. That'll give me negative 4 equals 1p minus 16. I add the 16 to the other side, and I get that p equals 12. Keep in mind, if you got a negative number, something might have gone wrong, but always plug it back in to make sure. If I do 3 times 12, I get 36, minus 4 gives me 32. So I have 32 degrees, which means the other angle must also be 32 degrees, so that means that they are acute angles.